University in Berlin will be telling us about some remarks on transversality and symmetry.
Since when? Since yesterday, maybe. Okay. Thanks for the invitation, and I apologize in advance for my handwriting and for the amount of chalk that's going to get destroyed over the next hour. So there's kind of a folk theorem that most of us have heard of before, that you can't have transversality and symmetry at the same time. And I want to talk about, first of all, in what sense that's concretely true. We're all familiar with one major example that comes up a lot in symplectic topology, that is the problem with multiply covered holomorphic curves. You can achieve regularity by making generic perturbations for simple holomorphic curves. For multiple covers, this is clearly impossible in certain situations where you can just see for dimensional reasons that it would lead to a contradiction. And then you have to be very creative with something like abstract perturbations or virtual methods, something that breaks the symmetry so that transversality is possible. I'm not going to talk about any of those clever methods. I want to talk about what you can do without breaking the symmetry, how you can recognize in what situations transversality is still nonetheless possible, and if it's not, then how you can prove whatever the next best thing may be. So I'll mention one other situation that most of us have heard of where actually equivariant transversality is just fine, and that is the fact that in a contact manifold, for generic choices of contact form, all the closed Rabe orbits are non-degenerate. So maybe you're not used to thinking of that as an equivariant transversality problem, but it is, because there's a distinction between simple Rabe orbits and multiply covered Rabe orbits. This is something for the equivalent statement in Floer homology doesn't really arise, because you're just looking at a time-dependent vector field, and there isn't this distinction between simple and multiply covered. But multiply covered Rabe orbits do have a non-trivial cyclic symmetry group. You can view them as the zero set of an equivariant Fredholm section, if you want to. And you'll find if you try to use the methods you've probably been taught to prove this statement, that generic contact forms make all the orbits non-degenerate, what you're able to do based on what you learned from holomorphic curve theory is prove that for generic contact forms, all simple Rabe orbits are non-degenerate. Now you can then go from simple to multiply covered in a second step, but somehow that second step depends in some crucial ways on the particular setup you're working in. So I want to introduce kind of a general framework for dealing with that second step in various problems. And I'll start with finite dimensions, not because it's particularly interesting to me, but because there are some easy examples we can see for how this works. So I'll first give you a very concrete example where equivariant transversality clearly doesn't work. Let's say we're talking about smooth functions from R2 to R2, and we're going to call f Z2 equivariant if it satisfies the following relation: f of x minus y equals minus f of xy. So what's going on there is that I have two distinct Z2 actions on R2, and I'm asking for these functions to be equivariant with respect to these two Z2 actions. So observation, right? Our domain and our target have the same dimension. So if you could say f is transverse to the 0 section, or just transverse to 0, meaning 0 is a regular value of f, I'll write it this way, f transverse to 0, then of course the 0 set will be discrete. And the second observation is that that's never going to be true, because from that relation you can see what's f of x comma 0, it's the same as f of x comma minus 0, which is then minus f of x 0, and therefore 0. So that's a one-dimensional submanifold, R times 0, which is contained in the 0 set of this function, no matter what function you chose. That observation depends only on the assumption that the function is equivariant. So the 0 set will never have the right dimension. It doesn't matter how generically you perturb this function, unless you break the symmetry. What you can nonetheless hope for, I'll call this the best case scenario, is a so-called clean intersection. Instead of asking for f to intersect 0 transversely, you can say f intersects 0 cleanly, which means that the 0 set is a submanifold, even if not having the right dimension. And that its tangent space at each point is what you would expect from looking at the linearization of f. In other words, Tx of n inverse of 0 ought to be, and certainly it always will contain the kernel of the linearization of f. We want those two things to be equal. So that's what I mean by clean intersection. And it's not too hard to convince yourself that in this particular example, that is an achievable condition. And that's true for generic choices of equivariant functions. That also follows from, I'll call this now a sample theorem, just because finite dimensional things are not really where I want to put my focus in this talk, and I haven't thought a great deal about what's the most general thing I could prove about them. But here's one thing that at some point I convinced myself is true. So if you like, you can think of this f as not just an equivariant function, but as a section of an orbibundle over an orbifold. Right? The orbifold would be R2 divided by one of these Z2 actions, and then the orbibundle has fibers R2 which have the other Z2 action acting. So let's generalize that notion and suppose E over M is an orbibundle over an orbifold M. And let's focus on the case where we have a 0 set with virtual dimension 0, which means the rank and the dimension here should match each other. So the rank of E equals the dimension of M, both of them finite. And now I'm going to add one more assumption, which is somehow totally artificial, but makes me able to prove what I'd like to prove, and is satisfied in that example. Suppose also that for all points in our orbifold, so every point in an orbifold has some finite local isotropy group. Right? So the neighborhood of that point gets identified with Euclidean space divided by an action of that group. Let's suppose that the isotropy group at every point has order at most 3. So it's either Z2 or Z3 if it's not trivial. And the conclusion is generic section sigma of the orbibundle intersect 0 cleanly. That's something you can establish as a generic condition. Okay, so we've seen transversality to 0 is something you can't achieve, but the next best thing you can actually do in this situation. I'll state one more sample theorem, which also is a very natural thing you'd want to prove if you think a lot about orbifolds. I should stress that well, I don't know whether anyone before me thought about this or figured out a proof of this. This one I know for sure that it's not due to me. There's a paper by Arthur Wasserman back in the 60s, and another one by Richard Hepworth in, I think, 2009. It's about equivariant Morse theory. And this is basically the first result you would want to prove if you want to study equivariant Morse theory, namely generic smooth functions on an orbifold are Morse, which in some sense is a finite dimensional version of what I said about non-degenerate Rabe orbits at the beginning. Yeah?
Let me guess. So is that weird condition on the isotropy have to do with representation theory and set 1, 2, and set 1, 3?
It has something to do with the representation theory of Z2 and Z3, yes. Namely, it's especially simple.
It's like the maybe condition of both theories and
It is a condition that makes me able to prove something. I don't know what the most general such condition would be. Okay. So let me now describe the main idea behind these before I move to infinite dimensions. So the first thing I'm going to say is that if I don't have some extra assumption like this about the isotropy group, or, I mean, the special thing about the Morse function example is that you're dealing with sections of a very specific orbibundles, the cotangent bundle. You're trying to prove that these sections of the cotangent bundle over an orbifold are transverse to 0. In general, I'm not going to be able to make any nice statements about the global structure of the 0 set of a section of an orbibundle. The best I can do instead is to break that set down into strata, which I can prove are smooth submanifolds. And that's not that hard to do in the first place. So let's say for generic sections of our orbibundle sigma, let's denote curly M of sigma. In other words, moduli space notation is the 0 set. So I claim, and this is something that's really not too hard to prove, that this is stratified by submanifolds, which I'm going to call Mg of sigma. So what's that? That's the set of all points x in the 0 set, M of sigma, such that the isotropy group at x is isomorphic to some given finite group G. So if you take the union of those spaces over all possible finite groups, each one defines some submanifold, which has a smooth structure in a natural way. And the disjoint union of all of those is obviously the 0 set. That's not very much information yet. And so far, this doesn't require really anything other than the usual application of the Sard-Smale theorem, if you're paying a little bit more attention to the symmetries on an orbifold than you usually would. The important part comes next, which is that each of these individual strata also contains further submanifolds. Let's call them walls. Mg of sigma indexed by some additional non-negative integers, k and l. So that's supposed to be the set of all points x in Mg of sigma, such that the dimension and coda is a dimension of the kernel and of the co-kernel of the linearized section at that point is precisely these numbers. Dimension kernel of d sigma at x equals k, and the dimension of its co-kernel equals L. So the non-trivial part here is one has to prove these are smooth submanifolds of Mg sigma with codimension, something that you can compute. And to compute it, you need a bit of representation theory, because it's going to be the dimension of some space of G equivariant linear maps, Hom G, of the kernel at that point to the co-kernel. Okay, so in general, of course, I should say this thing will have many connected components which may have different dimensions because it depends on various symmetry information. It depends really on representation theory, what precisely this dimension is, depending on how the isotropy group acts on the tangent space and the fiber at a given point. Now, this is all stuff that one can compute. So this is also not really hard to prove. The methods required for it are basically finite dimensional analysis plus a bit of representation theory plus the Sard-Smale theorem. Now, let me give you a one-line quotation mark proof of sample theorem 2. And that is simply, the point is dimension counting. You want to prove that for generic sections, satisfying, for instance, this condition here, all the critical points you have, in other words, all the zeros of the differential of your smooth function, will satisfy the non-degeneracy condition, which means that the linearization of that section, in other words, the Hessian, has zero-dimensional kernel and zero-dimensional co-kernel. So anything that doesn't have that property lives in one of these so-called walls here. You have to compute the dimensions of those walls, and what you find out in that setting is that degenerate critical points lie in walls of negative dimension. So generically, therefore, there are none. Let me add one remark about this, because it's another general application of the kind of ideas I'm talking about, but I'm not going to say anything beyond this remark. So those walls have negative dimension, but that doesn't mean they're going to be irrelevant in every situation. For instance, some of them have expected dimension -1. Now, that'll be relevant, for instance, if you want to talk about not a single smooth function, but a smooth one-parameter family of functions, right? Then the virtual dimension of your set of critical points jumps from 0 up to 1 because of the extra parameter. And then the codimension 1 walls become relevant, and you will see a wall-crossing phenomenon. So if you want to study bifurcation theory of critical points of Morse functions on an orbifold, that's what you need to pay attention to. So walls of dimension -1 will give you bifurcations under generic one-parameter deformations. Any questions so far? All right, that was the finite dimensional part of the talk. So let me state a couple of infinite dimensional theorems that have to do with holomorphic curves. So the general setting, yeah. These groups I'm talking about are always finite. Yeah. So in a moment, I will say something that involves a potentially non-discrete group acting on a manifold, except it acts also with finite isotropy. So again, the discussion comes down to orbifolds rather than whatever more general than that. So an example of an infinite dimensional setting is, of course, you talk about moduli spaces of J holomorphic curves in an almost complex manifold M of dimension 2n. Let's use a little bit more space here. And so let's say MGJ, that's the moduli space of unparameterized closed J holomorphic curves of genus G. So elements are tuples consisting of the surface of genus G closed, complex structure on that surface, and the map from that surface into M, which of course should satisfy various conditions like the Cauchy-Riemann equation, most importantly, possibly a homological condition if you want to specify that. And we're going to divide this by the equivalence relation given by reparameterization. Now, locally, let's say near a given curve, sigma g with complex structure j naught and map u naught, you can identify this with something that you will be able to prove generically, hopefully, is a smooth finite dimensional manifold. That's the zero set of the nonlinear Cauchy-Riemann operator. But then you have to divide that by a natural action of the group of automorphisms of the domain. So that's what I was referring to. This is a group that might not be discrete in general, but then it acts on this guy with finite isotropy. The isotropy is precisely the group of automorphisms of the given holomorphic curve. So that's where, right, if you can prove that this thing really is a manifold of the right dimension, you get an orbifold structure on the moduli space in this way. This thing, d bar j, is a function of both the complex structure and the map tu plus j of tu of j. All I'm going to say about this is that that is a Fredholm section of a certain infinite dimensional Banach space bundle. In particular, its linearization at each point is a Fredholm operator between Banach spaces. And then we say that an element in the moduli space, namely the equivalence class of curves sigma ju, is regular if and only if the linearization of this nonlinear Fredholm operator is surjective at that point. So the general theorem is, if you restrict to the open set of holomorphic curves that are regular in this sense, that set has a natural smooth orbifold structure. But of course, we can't achieve that in general. So theorem 0, I'll call it 0 because this one is not due to me at all, that's just completely standard, is that if you pick J to be generic, then all the so-called simple curves are regular. So simple means not multiply covered, and in particular that means there is no symmetry. There's no automorphisms of those curves. So that's where symmetry doesn't cause any problem because you're assuming it away, and therefore transversality is possible. So what's somewhat more surprising, and this is tricky. I have to say this is a theorem due to me from something in the convex hull of 2016 to 2019, because it appeared in the archive with an incorrect proof in 2016, which was recognized as incorrect in 2018 and corrected in 2019. That's the complete truth. So again, same assumption, J is generic. Then also not just simple curves, but all unbranched covers of simple curves are regular. And then theorem 2, same attribution. So I mentioned before, for branched covers, it's in most situations hopeless to achieve transversality, and you can see it for dimensional reasons, because in a neighborhood of your multiple cover, there's always some obvious manifold of nearby curves that you can see, because the underlying simple curve lives in a moduli space of a certain dimension, and the branched cover also lives in a moduli space of a certain dimension. Add those up, you may get something that's too large for the virtual dimension of your curve. So then you know transversality is impossible. But there are certain situations where you can hope for something nice to be true anyway, and one of those is this setting of so-called symplectic Calabi-Yau three-folds or six-folds, depending whether you're thinking complex or real. So let's say if J is generic and the dimension of our almost complex manifold, the real dimension is 6, and its first Chern class vanishes. I don't think I have to assume M is closed in any of this, but I'm talking just about closed holomorphic curves at the moment. So this is a situation in which all holomorphic curves have index 0. Virtual dimensions of all the moduli spaces are 0, which means for branched covers, transversality is clearly hopeless. Turns out the next best thing is true, which is that for generic J, this nonlinear Cauchy-Riemann operator, d bar J, intersects the 0 section cleanly. And that's one way to express a condition known as superrigidity. So that's something that especially had been talked about in the algebraic geometry literature by people like Pandra, Panda, and Bryan since about 2000. And there's this collection of results telling you what kind of nice properties the Gromov-Witten invariants have if the superrigidity hypothesis holds. But it's known not to hold in the algebraic category in general. So this is a statement about the symplectic category with generic almost complex structures. And in fact, I can even guarantee you with certainty that my almost complex structures here are not integrable. So this is somehow separate from the complex category. But for instance, you get corollary using a few results of other people like Alexei Zinger, that the Gromov-Witten invariants, so each of the Gromov-Witten invariants in this setting, they're just numbers, right? They're trying to count the number of holomorphic curves you would expect to exist after some abstract perturbation that makes them all transverse to 0. You can compute this actually as a finite sum over some finite collection of embedded curves of some Euler numbers of well-defined obstruction bundles. So in particular, for each homology class in each genus, there's just a finite collection of embedded and actually generically disjoint holomorphic curves which contribute to the Gromov-Witten invariance, but they contribute in a sort of interesting way. You look at the moduli space of all the multiple covers over those particular embedded curves, and the co-kernels of the linearized Cauchy-Riemann operator for each multiple cover all have the same dimension due to this clean intersection condition. So they form an Orbi bundle whose Euler class you can then compute to figure out these counts. So that's all I'm going to say about the applications. I want to try and describe the ideas behind the proof. Yeah? Eleni, why is it called superrigidity? Right, so there's a weaker notion that's talked about sometimes called D-rigidity, which basically is the condition that this is true for multiple covers up to degree D. So if it's true for all D, that's called super-rigidity. Yeah. I mean, one can state this a little bit more generally. So what I know how to prove in general is that if M has dimension at least 6, then all multiple covers of index 0 simple holomorphic curves satisfy this condition. So this is just the short. It's the same proof. Yeah. I mean, this is just the useful special case. I'm not sure what to do with the other cases. Okay. So for the rest of the talk, I want to give some general principles of what to do with equivariant differential operators. And this would actually be a good moment to mention a couple of other people who've been trying to generalize some of this stuff to other contexts beyond holomorphic curves, namely Alexander Dwan and Thomas Walpurski. Have a paper on the internet talking more generally about elliptic differential operators and how to understand equivariant transversality problems. So some of what I'm going to say is a result of my discussions with them. I want to consider two vector bundles over the same manifold sigma with a differential operator D. So a linear map from the sections of E to the sections of F, first order. And for most purposes, one needs to assume elliptic, but I don't really need to say that in setting up the problem. But I do also want to assume there's some equivariance in the picture. So let's assume that this operator is equivariant with respect to actions of some finite group G, acting on both of the bundles and on the underlying manifold. So in particular, this is what you have if you study the linearized Cauchy-Riemann operator along a multiply covered holomorphic curve. And the finite group in that case will be either the automorphism group of the curve or in general, maybe the automorphism group of some regular cover that factors through that particular cover. So I want to only prove things about what can be done with local perturbations in some region, right? It should be true that if I can achieve some nice transversality-like condition by perturbing J in some region, it should be true for all the curves that pass through that region. So let's specify a region where perturbations are allowed. U is an open subset of sigma, which is also G invariant. And then we're going to define the space of equivariant zeroth order perturbations. Namely, these are the things that will arise by doing something like perturbing the almost complex structure. So what I'll call AG of U is just the space of smooth bundle maps. So sections of the bundle HOM from E to F which are also G invariant and with support contained in this subset U. Sorry? Sigma is closed, yeah. So a lot of what I'm saying also can be generalized beyond that, but I'm going to stick with the closed case for this talk. So if you have an element A in that space of zeroth order perturbations, you can just add that to your differential operator and have another differential operator, which is, since we're talking about the closed case, that'll be a compact perturbation of your differential operator. It'll have the same index if it's Fredholm. So I'll call that one D sub A. It's just D plus A. And now I can ask the technical question that needs to be answered if you want to apply this strategy I outlined in the first half to something like the holomorphic curve problem. Namely, is the following set. Let's define AG sub KL of U as the set of all zeroth order perturbations A such that the dimension of the kernel of dA is K and the dimension of the co-kernel of dA is L. Is that a finite codimensional submanifold of the space of zeroth order perturbations? So in case anyone in the room is as concerned about analysis as I usually am, you might complain at this point that I'm talking about finite codimensional submanifolds of things that maybe aren't really Banach manifolds technically. So one has to take some Banach space completion instead of just talking about smooth bundle maps. My favorite would be the Flourcy epsilon space, but there's other things one can do. I'm not going to specify that here. Okay, anyway, the question clear. Right, so of course, we're talking about Fredholm operators. So this dimension, these two dimensions will be finite in general, but we want to single out the space of operators for which those dimensions have fixed values. So what does one need to prove something like that? Let's suppose, without loss of generality, let's take D to be in that space. I can, right, if I find anything in that space, I can just redefine my reference operator as that one and look at small perturbations of that one. So take D to be in the space AGKL of U. So I didn't say this earlier, but I stated this formula for the dimension of sort of the equivalent thing, or the codimension of the equivalent thing in finite dimensions before. You get this by the following thought process. Right? There's a nice sort of exercise that I like to assign to well-motivated students in a differential geometry class that says, given positive integers m, n, and k, prove that the space of m by n matrices with rank k is a smooth manifold in a natural way and compute its dimension. Okay? So how do you do that? In general, if you're talking about matrices, as linear maps between finite dimensional spaces, if you have an element that's in that subspace, then there's a natural map you can write down that's defined in a neighborhood of that one, which takes values in the space of linear maps from the kernel of that matrix to the co-kernel of that matrix. So that's something I wrote down some version of that earlier in finite dimensions. You can do the same thing in general with Fredholm operators. So what's true here is that there exists a neighborhood of 0, I'll call it curly O, in the space of G invariant zeroth order perturbations, and a smooth map. Yeah. Oh, sorry. Yeah. I meant 0 when I said that. Thank you. So yeah, D has, in particular, these properties. That's what I really meant. So we have a neighborhood of 0 now, and a smooth map, phi from that neighborhood to the space Hom of the kernel of D to, I could write the co-kernel of D, but it'll be more convenient right now if I talk about the kernel of the formal adjoint of D, which is isomorphic. So we have to choose bundle metrics and an L2 pairing for sections and define the formal adjoint. And that's isomorphic to the co-kernel of D. I do have to pay attention now, very important, to note that this map has its image not in this rather large space, but in a subspace of it, because there's this G action floating around. So these guys will automatically be G equivariant. I have to put Hom G here. Okay? Such that a neighborhood of my hopefully submanifold is exactly the 0 set of this map. So now the problem is reduced to the implicit function theorem, right? We need to linearize this map, and hopefully that linearization at 0 will be surjective, and then we get what we want. Then this guy will be a submanifold, and its codimension will be exactly the dimension of this space here, which is some finite dimensional vector space. You can compute its dimension using representation theory. So what's the linearization? Its linearization at 0 is, let's call it L, so d phi of 0. That's some linear map from, well, the tangent space at 0 to this guy. This is just an open subset of this, so it's that space of G invariant 0th order perturbations again, sending us to Hom G of kernel to co-kernel, or kernel of formal adjoint. And what we can write down this operator explicitly. It takes the form, plug in some 0th order perturbation. L of A should be some linear map from kernel to kernel D star. Specifically, if you feed in a section eta in the kernel, what you get out of this is you have to multiply this bundle map by eta, so now you have a section of the other bundle F. Now, you have to project that into the co-kernel. So I'll call this pi of A eta. Here we have the L2 orthogonal projection, pi from the L2 sections of F to the kernel of D star. So that's what the linearization is. And the rest of what I have to talk about surrounds the question, is that operator surjective? So I'll mention a bit of history. I mean, this kind of operator has appeared in the literature at least a few times before. So I recognize this in a paper of Taub's in the 90s that introduced the Gromov invariant, where he had to also do some kind of equivariant transversality problem for multiply covered tori. It also appears in the paper of Eleni with Tom Parker on the Gopal-Kumar-Vafa formula, because they have to do a wall crossing argument. And you need to know that the walls have a sufficiently nice structure to understand what happens when you cross them. So in each of those papers, I think what's been done is to prove some weaker statement than what I'm trying for here. It does not prove that this linearization is surjective, and it does not prove that this thing here is an actual smooth submanifold. But it's something a little uglier than a submanifold that is good enough in those situations to get the job done.
In our first paper, Taub's paper, there was like extra information to get you forward.
Yeah. I mean, whatever you can prove, whether it's good enough, tends to depend on various bits of representation theory and other things that are specific to the situation. Well, I'll tell you in a moment why I really do want that operator to be surjective and not something weaker. So this is the new question. Is L surjective? So my first remark about this is that if you can prove this while ignoring the equivariance, so just remove G from wherever it appears over here and talk about this linear map defined from the space of all zeroth order perturbations that are not necessarily G invariant to the space of all not necessarily equivariant linear maps from kernel to co-kernel. So if you can solve the problem in that situation, then it also works equivariantly. And the key word here is you have to symmetrize. In other words, if you can solve the problem non-equivariantly, that means now given anything that is in Hom-G of kernel to co-kernel, you can find a not necessarily G invariant zeroth order perturbation that L sends there. Okay? But now you can act on that solution with the G action. And since this is a G equivariant map, you'll get other solutions that way. And then you can take the average of those over this finite group. You can symmetrize, and that way you get a G invariant solution. Now that's something that you only have any hope of doing if this map really is surjective. If it's some weaker condition you're trying to establish, then going from the non-equivariant to the equivariant case, I really have no idea what to do. And believe me, I have thought about it. So that's why I really want to prove something a little bit stronger than what had been done before. All right, how do we prove it's actually surjective? Now we're just going to look at the non-equivariant case. So it doesn't seem improbable that it's surjective, right? Because you're mapping an infinite dimensional vector space to a finite dimensional one. So that looks like it should be doable. Let's choose orthonormal bases of the kernel and the co-kernel. So eta 1 through eta k of kernel D and psi 1 through psi L of kernel D star. Then in this choice of bases, you can express any linear map from kernel to co-kernel via its matrix elements. That means for any A in this space of zeroth order perturbations, L of A, that's a linear map now, not necessarily G equivariant, from kernel D to kernel D star, has the matrix elements L of A acting on eta I paired with psi j in the L2 pairing. So now you think about what is that. According to this formula over here, I just act with the zeroth order perturbation with the bundle map on eta. I get a section of F, and now I have to project it to the co-kernel. But that's the L2 orthogonal projection. If I'm then taking the L2 product of that with something that's in the co-kernel, right, I added some stuff that's orthogonal to that, but it doesn't matter. I can forget about that projection now. This is the same thing as L2 product of A eta I with psi j. So those are the matrix elements. Those are, in effect, the coordinates of L of A in a certain basis for a given A. So now, if L is not surjective, what does that mean? It means there's going to be some non-trivial element in Hom kernel to co-kernel that's orthogonal to it. One way to say that is, well, if L is not surjective, so I can express this orthogonal element just as a bunch of matrix elements, meaning there exists constants Cij real numbers, not all of them 0, which will be orthogonal to L of A for all A, meaning for all A in the space of zeroth order perturbations, 0 equals the sum over I and j of Cij times this matrix element. All right? So let's unpack a little bit what that actually is. These L2 products are actually integrals. And, well, since A is assumed to be supported in this open subset U, I just have to integrate over that subset U. Integrate the bundle metric of A eta I with psi j at every point over the chosen volume form on sigma. And, well, think about it this way. This bundle metric, so this is a bundle metric on the bundle F, that's a bilinear map, so bilinear bundle map from the tensor product of F with itself to some trivial vector bundle. Let's express it that way. Integrate, let's regard that bundle metric as a bilinear bundle map. Now I need to apply this operator A to eta I. That means we have a bundle map of the form A tensor identity acting on some section of that tensor bundle. What section exactly? Here I can include the summation and define sum of Cij times the section eta I tensor psi j. That's what I'm actually integrating. So this thing here, that's a section of the vector bundle E tensor F. And now you can see one situation where there's obviously a big problem. It might be true that that section vanishes identically. Or it just, on this open subset U, it might vanish identically. Right? If that's true, then this thing is always going to be 0. You don't get a contradiction. What's not actually too hard to prove, it's an easy lemma, is that what I'm saying here actually happens if and only if that section vanishes identically on U. If there's just one point where that section is non-zero, then you're all right. Then you can make a choice of this zeroth order perturbation A supported near that point, kind of the same way. This is analogous to the step in the normal story of transversality for holomorphic curves, where you applied the similarity principle to show that sections in the kernel of a Cauchy-Riemann operator satisfy unique continuation, so they can't vanish on an open subset. And now you find some point where it doesn't vanish, and you choose your perturbation to be supported near that point, and make sure that this number can't be 0. This is really the same idea, what's happening here. The new feature is right now I really don't know whether this section here is 0 or not. And that looks in some ways like a unique continuation problem. That's how I thought of it in the beginning. But I was wrong, and that has a lot to do with this spread of 2016 to 19 that I was talking about. So let me tell you what is correct. First, this discussion leads to a definition which, at least the terminology for this definition, I have to attribute to Vianna and Valpuski. This is something that they adapted from the algebraic geometry literature. We'll say that our operator D satisfies Petrie's condition. If the natural map, or let's say in particular Petrie's condition on the subset U, if So there's this natural map from the kernel of D, tensor kernel of D star, to the space of sections of the tensor bundle restricted to our subset U. So this map is defined in the most naive way possible for a product of two. So I'm going to call this map pi u, and we define pi u on a tensor product of two sections, eta and psi. That needs to be a section of this tensor bundle. Its value at a point z will just be the pointwise product of the values of eta and psi. So the condition is I need this map to be injective. In other words, as long as I have a non-trivial element of this tensor product, which is equivalent to having some set of coefficients Cij here that are not all 0, and then taking this kind of linear combination, then I send it over there and make a section of the tensor product bundle out of it. There's going to be some point on U where that section doesn't vanish. That's Petrie's condition. Yeah? Yes, I'm about to. Let me take a quick poll first. How many of you feel you have some sort of intuitive understanding of what this condition means? That's what I thought. That's also how I felt when I first ran into it. So I'll give you a couple of examples. First, here's one where it always holds. Remember, we're not specific to Cauchy-Riemann operators right now. I can talk about any differential operator I want. So let's say we take the underlying manifold to be one-dimensional, S1. Now, elliptic differential operators on S1 are quite simple. You just need to make sure that the first-order term is not 0 at every point. For instance, if you take d to be just the derivative with respect to the one coordinate and add any 0th order perturbation you want, that always satisfies Petrie's condition. And the reason is your PDE at this point is just an ordinary differential equation, right? Local existence in uniqueness tells you if a solution to that equation is 0 at some point, then it's identically 0. A corollary of that is if you have some set of solutions that are globally linearly independent, they're also going to be pointwise linearly independent at every point. So that's another way of saying take some non-trivial element of this tensor product here and look at it as a section of this tensor product bundle, right? At every point, you have a bunch of linearly independent things, which will therefore give you something non-trivial in this bundle. So in fact, over here, you get something that's nowhere 0, not just non-vanishing at some point. So that actually has interesting applications. Once you know this, you can apply this general framework I've been sketching and work out wall-crossing phenomenon for Rabe orbits, for example. Right? Because this is the type of linear differential operator that arises when you linearize the Rabe flow equation. Or you could regard asymptotic operators as equivalent to these. Okay? So that's one thing one can do. Now to answer Augustine's question, here's an example of, in fact, a Cauchy-Riemann operator. Take our domain to be just, say, the disk, and take the operator D to be the ordinary D bar operator acting on the trivial line bundle over the disk. So its formal adjoint will be minus the D operator, or the partial operator, which means solutions to this equation will be holomorphic functions. Solution to this equation will be anti-holomorphic functions, functions of Z bar. Now, here's a tensor product you can cook up, if you think about it a bit. This map pi, the so-called Petrie map, I'm going to act on, so 1 is a holomorphic function. IZ bar is an anti-holomorphic function. I is a holomorphic function. Z bar is anti-holomorphic. Then Z is holomorphic, and I is anti-holomorphic. IZ is holomorphic, and 1 is also anti-holomorphic. And I stress these are all real tensor products, right? Even though Cauchy-Riemann operators are defined on complex vector bundles, they are real linear operators in general. So this whole discussion, all the tensor products are real linear. And for that reason, this tensor product here is a non-zero element of kernel D tensor kernel D star. But when you work out what this thing is pointwise, you get something identically zero. All right, so that's your counterexample. And that's, in some sense, the bad news if you want to apply this equivariant transversality idea to holomorphic curves. It's not going to work for arbitrary Cauchy-Riemann operators, and in particular, it's not going to work when J is an integrable complex structure, because then you get Cauchy-Riemann operators that always locally look like this one. They're complex linear. The good news is, of course, we're still allowed to perturb J, make it non-integrable, and make our Cauchy-Riemann operators not complex linear. So I'll end with the statement of a theorem. This is going to play kind of the same role that Roget's Whitney trick played yesterday. It's the theorem on which everything else depends and that I have no time to explain really at all. We can summarize it by saying Petrie's condition is generic for Cauchy-Riemann operators. So namely, I'll state a slightly more technical version of this than really necessary, just so that you can imagine a little bit what goes into the proof. The statement is for all points z in our perturbation domain and all natural numbers L, there exists another natural number k greater than or equal to L, and a bare subset, call it CRL, in the space of all Cauchy-Riemann type operators, such that for all operators D in this set, if I have an element T in the tensor product kernel D with kernel D star that does not vanish to order L at Z, then plugging in that tensor product to the Petrie map, so I get a section of a certain tensor product bundle, pi of T, also does not vanish to order K at Z. In other words, some partial derivative of order less than or equal to K of this guy at that point will be non-zero, given that I've chosen some linear combinations of sections of kernel D and kernel D star, which also have the property that some partial derivative up to order L is non-zero at that point C. So the unique continuation phenomenon is built into this, right? If we didn't know unique continuation, then this statement would be useless, because then you could still take some non-trivial element of this tensor product, which vanishes to all orders at that point, and you wouldn't get any result. But we know at every point, whatever non-trivial thing you have in here, it's not going to vanish to all orders. There's going to be some L large enough that it doesn't vanish. And then plugging it into the Petrie map will also produce something that is not going to vanish to all orders at that point, and therefore will be non-zero somewhere on a neighborhood of that point. Okay, I'm over time already, so if you actually want to know something about the proof, talk to me over lunch or something. Thank you.